ascending. There's your 300 milliosmoles. And remember, I said that the proximal convoluted tubule has a concentration of 300 milliosmoles at the very beginning. And yet at the very end, it's the same value because we lost both solutes and water. And we can see that because here's the actual value at the very beginning of my loop of Henle. It's the same number. Now what happens to the concentration as we go down the loop? What happens to the concentration? Why is it increasing? Right, because water is leaving, right? And that means you have to have lots of aquaporins in those cell membranes. Now, I'm hoping you can see that as water leaves, and only water leaves, it makes the concentration become greater. Y'all agree with that part? Yeah? All right. So, why would water be leaving the filtrate and going into the neighboring tissues? Why is water leaving here and going in there? You know the answer, you just may not know that you know it. Why does water go anywhere? So what about concentrations? Does it go into more hypo or more hypertonic environment?
Hyper.
Hyper. That must mean that for every segment of that descending limb, if you were to compare the concentration right there, then this has to be more hypertonic than that is. So if that's 600, maybe that's 610. Wherever water is going, that must be more concentrated than that part of the tube. If that's 900, then maybe this is 910, right? They have to be a little bit offset so that water always goes from the more concentrated area of water to the more less concentrated region of water. But no ions can leave. So by the time we get to the bottom of the loop, we're at 1200 milliosmoles. That's pretty concentrated. But now we go back up. We're now at the thick portion of the ascending, where there are no more aquaporins. That means it's not permeable to water. But you have lots of transporters for ions. We have one that's actually a very busy protein structure. It's moving a sodium, a chloride, and actually a potassium ion. This is actually this right here. This is a more accurate description of that, right? This is our thick ascending. See the lack of microvilli? And this green transporter is this transporter here. They just simplified it over here. So let's look at what's actually happening in the ascending segment. This is your apical membrane. This would be the basal membrane. The basal membrane is the only place you find your sodium, potassium, ATPase pumps. The basal membrane is the only part of the cell you will find your sodium, potassium, ATPase pumps. How many sodiums does a sodium, potassium, ATPase pump move?
2.
How many sodiums?
3.
How many potassiums?
2.
So that means they're abbreviating. They're not showing you the actual number. Do not think this is a weird pump. They should have put 3 sodiums and 2 potassiums in there. They didn't. So if you have trouble remembering that, write that in now. Right? 3 sodiums get out, and 2 potassiums are always brought in, and it costs you 1 ATP to do that. Now this green thing is a symporter. It's doing facilitated diffusion. No ATPs required. And look what it's doing. It's like a really big carnival ride. It has 2 seats for 2 chlorides. It has a seat for potassium and a seat for sodium. And if you notice, 1 plus and 1 plus equals 2 pluses, right? And there's my 2 minuses. I don't change the membrane potential. But the bottom line is this. I'm taking chlorides, potassiums, and sodiums out of the filtrate and facilitated their transport into the cell. And then what do? I transport the chlorides and potassiums through another symporter, another facilitated diffuser, but I'm pumping the sodium out. but it just so happens that this is an antiporter, and so the potassiums that got diffused out get pumped right back into the cell and diffused right back into the filtrate. They make a complete round trip, which is why they don't show it to you here. In a sense, there's no potassium loss. All we're really losing are sodium and chloride ions. We're not losing the potassiums, right? Because the potassiums, they come in, but then they get pumped right back into the fluid. So all we're really losing are the sodiums and chlorides. And when you lose those solutes, when they come out of the filtrate and you don't lose water, the filtrate becomes less and less concentrated as we work our way up the tube. At the top of the tube, on the right hand or the anatomical left hand side, right? That filtrate compared to this filtrate, on the left or the right, which one's more concentrated? The one on the right in the red region, right? This one is more dilute. That's important. In a sense, this is more hypotonic than that is. That extra water that is in that filtrate, your kidneys will use if we need to raise your blood volume or to conserve water. If you don't need to raise your blood volume and you don't need to conserve water, that is what gives you large volumes of clear, dilute urine. That's the water you don't need, so you're going to pee it right out. When you guys start noticing your maturation process, a fancy word for peeing, right? Start noticing your urine, right? And we don't stare at it and dilly-dally over it, but you want to notice its smell, right? And its color, right? Am I having large volumes of clear? That means I'm well hydrated. Is it dark yellow and kind of salty smelling? That means I'm a little on the dehydrated side, right? And you tend to notice being a little more thirsty when you tend to have more concentrated yellow, salty smelling urine. When you have more concentrated yellow urine, that number is a lot larger. There's more solutes in there. You're more dehydrated. All right? We will pick this up again on Wednesday, ladies and gentlemen.